All right, let's try out this problem called maximum number of toys. So what is given in this problem? Well, in this problem, first we are given an array of toys, a cost of each toy, right? So let's have a quick read. So you are given n toys in a shop. The cost of each toy is represented by some array. You are given q queries. Now, in each query, what is given to us? There is a bunch of information that is given to us for every query. One thing is the first thing in the query is the total budget that we have. Second thing is if there are any broken toys, and if there are, what are the broken toys? And the thing is, we won't be buying any broken toys. So after removing the broken toys, whatever different toys are left, we'll try to buy them within the budget that is given to us. And our goal is to find the maximum number of not broken toys or the good toys that we can buy for each and every query. So let's look at this example to understand the problem better. So here, this is the costs array, and the first query is, if you have to read the query, the first query is your total amount is 12. There are two broken toys, and those are toy number 3 and toy number 4 based on one base indexing. Second query is, well, your total budget is 30 and there are 0 broken toys, right? Let's try and understand this example on a whiteboard. Right, so these are the different toys or the toy costs, right? So the toy costs are 8, 6, 9, 2, and 5. And it says we have to consider one based indexing. So that means this is toy number 1, this is toy number 2, toy number 3, toy number 4, and toy number 5. Now query number 1. So query number 1 is 12, 2, 3, 4. What is all it? So it says your total budget is 12. And it says there are two broken toys. And the two broken toys are toy number 3 and toy number 4. So toy number 3 is broken, toy number 4 is broken. So you can remove these toys, right? So now you're left with toys 8, toy number 1, and then toy number 2, which is cost 6, and toy number 5, whose cost is 5. So this is your total costs, and now your budget is 12. So with this budget of 12, how many of these toys you can buy? Well, if you think about it, if you look at it, if you buy this guy and if you just buy this guy, your total amount spent will be 11, which is less than 12, and that's the best that you can do. So for the query 1, with the remaining good toys, I can buy 2 of them. So that's the answer for query 1. What's query number 2? So query number 2 is 30, 0, meaning your budget is 30 and there is no broken toy. So what will be the answer for that? Well, it so happens that in this case, if you buy all the toys, so it will 8 plus 6 plus 9 plus 2 plus 5. This is actually 30. And your budget was also 30, so you can buy all the toys. So in this case, the answer is 5. Now that's all good. But what if this sum was less than 30 or more than 30? Sorry, yeah, if the sum was more than 30, how would you optimize? How would you solve this problem? So there are a lot of complications here, right? So there is initial cost. You have to figure out within a given budget how many toys you can buy, and there's extra complication. You have to do it multiple times for each and every query, and in each and every query, you are removing some number of toys. Let's simplify the problem first. Let's look at a simple problem where, well, we are given the array of costs and we are given the budget. And how do we just solve just based on that, right? So let's try and solve for that first. So we take a simple example. So let's say our costs array or toy cost is, let's say, 137, some random example. And the only thing is, okay, so these are my different toys, and let's say my budget is 20. Now how can we solve this? So if you just add all the costs here, it is 3 plus 1 4 plus 1 7. Sorry, 3 plus 1 4, 7 plus 4 11, and again 11, so 22. So we can see the total. We can't buy all the toys. We can only buy because buying all the toys will need 22, but we only have 20 cash, right? So how do we solve this? Well, let's discuss two approaches to solve this problem, and then we'll add the complexity of broken toys. So, well, essentially the goal is what? The goal is to maximize the number of toys, right? How can you maximize the number of toys? Well, it's simple, right? Buy the cheapest toy, right? If I want to get more toys, I will buy the cheaper toy. So what does that mean? That means we can maybe sort the costs array, right? And then it will become 1, 1. Maybe let's add one more just for fun. Okay, so let's add this. Just make it big array, but and then the sum is 33 and our budget is only 20. So then it becomes 1, 1, 1, 3, 3, 3, 7, 7, 7. And now the only thing that we have to do is just keep adding from left to right, and as soon as till your sum is less than 20, and if your sum becomes more than 20, then you stop. Okay, so 1 plus 1 2, 2 plus 1 3, 3 plus 3 6, 6 plus 3 9, 9 plus 3 12, 12 plus 7 19, 19 plus 7 will cross, so we stop here. So how many different toys did we collect? 1, 2, 3, 4, 5, 6, 7. So the answer is we can collect 7 toys. So what's the approach? It's a greedy approach where we are greedy and we're trying to buy the cheapest toy. So we sort and keep adding till sum crosses budget. Right? What's the time complexity of this approach? Let's talk about that. So it's very simple. Depending upon your cost array, if you have to sort it, it will be n log n, right? And then you run through the array once, so that's plus n. So that's the time complexity. You can also think about doing this problem using a priority queue. So you could put all the elements into the priority queue, and then you keep taking element out of it, priority queue, which will be the smallest, and then the next one, the next smallest. You get the same time complexity. Now the thing is, now let's add that complexity of the breaking of the toys breaking and everything. Now, if the toys are breaking, that means your costs array has to change. And because the cost array has to change, you might have to just repeat this process. And so if there are q queries, your time complexity might just become q times n log n or something like that, which if you try this approach, it will break and you won't meet the time limits needed. But okay, that's the sort of the limitation of this approach where you can't use it for multiple queries, because for each query you have to update or you have to remove certain elements from your array. Removing certain elements of your priority queue is not that optimal. Now, let's first also talk about another approach, which would be slightly tricky, slightly different, but let's hear me out. So let's take the same example again. So we have the same example. So we have the costs array, which is 137, 137, 137, and our budget is 20, right? Now, earlier you were looking at the array based on the individual toys. Now, let's look at the array based on individual costs. So what's the maximum cost? We can find out the maximum cost by just doing a single pass. So the maximum cost is 7. So now what I'm saying is let's consider each and every cost from 1 to 7. And this by definition is sorted, right? It's by definition, you would first, like we discussed in the previous approach, we first want to take the smaller guy, the smaller cost toys, then the next bigger, right? So we fix that implicitly, inherently by considering costs itself. And now let's build these different arrays. So I'm gonna build, so this is my cost, and now what I'm gonna do is I'm gonna use this cost as index. So, and again, so my cost is 1, my cost is 2, Cost can be 3, cost can be 4, cost can be 5, 6, and 7. The maximum is 7, so I build it till there. Now let's do this. Let's add for each cost, let's add this frequency array. And let's also add the an amount array. So what is the frequency? So for cost 1, let's go through these costs, and we see okay, so for cost 1 we see one guy, then next guy is at cost 3, so we update that frequency, then the next guy is at cost 7, we update its frequency, then we get 1 again. Well, so then we can update its frequency to 2, right? And so on and so forth. Essentially, if you do one pass, we figure out that what you have is there are 3 toys of with cost 1, there are 3 toys with cost 3, and there are 3 toys with cost 7. And for all other costs, there is no such thing. And what about the amount? So amount here is for this cost, if I have to buy all the toys, how much amount I will pay, right? Because that's what I'm gonna do, right? If I think about it, implicitly I'm being greedy. First I'm trying to buy all the toys of cost 1. Then I will try to buy as many as I can of cost 2, right? And so what's the amount here? So amount is just multiply frequency and cost, right? So I will be paying 3 amount here, 9 here, and 21 here, and everything else because there are no, right? And now let's do this. Let's add cumulative frequency and cumulative amount, because both of these, if you think about it, will be always non-decreasing, will only be increasing or remaining same, right? So here the cumulative frequency is what, 3. So now you have bought 3 toys. Here your change is to 6. So far you have bought 6 toys, and if you buy these 3 toys as well, then you would have bought 9 toys. Similarly, cumulative amount, you would have amount uh, dollars or rupees here, right? You will have spent 3 here, 3 here. Then at this point you would have increased it to 12. You have spent 12 amount of money, and then here you would have spent 21 plus 12, which is 33, right? And all of this, if you think about it, we can do it in O of max cost, right? Now, what can we do to actually solve for this budget thing, right? So to solve for this budget thing, let's try and find out how many for how many costs we can buy the all the different toys that are there. So we do a binary search on this cumulative amount array, right? So we see that in the middle we find that 12. So till cost 4, I spent just 12 rupees, and everything is good, right? So I go towards the right, I go towards the right. Finally, what I find is, except this last guy, like till this guy, everything was good. I only spent 12 amount of money. So, and by this, if I can look at the cumulative frequencies, I've already bought 6 toys for $12 or 12 rupees, right? Now, what was the budget? Well, the budget was 20. So what is the remaining? Remaining equals to 20 minus 12, which is 8. So I have 8 amount of money left, and the cost is 7, which is the one where I had problem. And because the frequency was higher, frequency was 3, so I could not buy all the toys with at this cost. But how many maximum I can buy? Well, that would be the remaining divided by the cost, right? So I can buy one more toy here. So the total number of toys that I can buy is 6 plus 1, and the answer is 7. That's another way to solve this problem. So really, in this approach, what we need is this cumulative amount and its cumulative frequency, and using the costs as the index. Now let's think about whether this problem can be scaled if there are multiple queries. Well, if there are multiple queries, then everything will change, right? The frequency for each cost might change. And so the cumulative frequency might change, the amount might change, because you have to remove the broken toys. Let's say one of the toy of cost 3 was broken, then this frequency will change from 3 to 2. that would mean everything changes. The cumulative frequency from here on changes. The cumulative amount from here on changes. So we need to be able to use this approach over multiple queries. We need to be able to do few things optimally, which is one is cumulative sum and update, right? So one is update and other is cumulative sum. Can we do these optimally over multiple queries? And the answer is yes. There are data structures that can be used to do update and prefix sums optimally. Like one of the example for that is you can use a segment tree. Another example is you can use binary index tree, which is also called Fenwick tree. And what these solutions provide is the capability to do both update and sum in log n time. Like usually what you the way that you would have either your update will be O of 1 and the cumulative sum would be O of n. Like one of them would be either O of 1 and the other one would be O of n. But if you have mix of update and cumulative sums, mix of like range updates and range sum queries or prefix sums and update queries, and you want to do both of them optimally, you can do it in log of n time using either of these two data structures. And primary index tree is slightly better because its performance is slightly better. Its space utilization is slightly lesser than segment tree. We're going to use this binary indexed tree in this problem. And I would recommend at this point for you to go and have a read about this binary index tree. I have a previous video. You can refer that, which I'll link. Now, but essentially, from the point of view of this problem, what you have to focus on is this. We have to be, so essentially we'll use this binary index tree for certain operations and only two of those operations. One is we want to find the prefix sum or cumulative sum till a specific cost, and we want to be able to find the frequency sum till a specific cost, right? That means how many total elements are there, how many total toys are there till this cost. So these are the operations that we need for some. Other thing is we also want to be able to update. This update is because of broken toys, right? So what this means I want to be able to update the amount spent till a cost and similarly update the frequency for a cost, right? And that could be because I want to remove certain broken toys. And this capability to be able to do optimally can be provided by binary index tree. And we'll use that and we'll use this approach where we essentially use the cumulative amount and cumulative frequency to find the first. Basically what we're trying to find here is we find the first guy or the first cost which requires where the cumulative sum is greater than the budget, right? That means till the previous guy, I could buy all the toys. So for till cost number six, till cost six, I could buy all the toys, and the number of toys was also six. But for cost seven, I could not buy all the toys because my remaining amount was just eight, and the required amount was 7 times 3, which is 21, which I did not have. And so what I did was how many maximum I could buy, I would have bought that. Like let's say instead of the 7, if this was 12 and my remaining was 8, then it does not matter because my minimum is 12 and I only have left with 8. I could not have bought any further toy and would have returned there. But that's the general idea. So let's using all of this that we have discussed, let's try and write the code now. All right, so we come to the code. So first I'm going to write a basic data structure for the binary index tree or a Fenwick tree. So let's first build that. So we'll have a Fenwick tree, and we're going to give its size as, let's say, n, and let's say there is a public constructor called Fenwick tree, int n. We're going to do this dot n equals to n, and we're going to create and keep an array, or we can call it tree, and we'll do this dot tree equals to new. So we'll do the indexing from 1 to n. So that's why we'll create an array of size n plus 1, and that's it, right? And the capability that it will provide, one of the capabilities it will provide is I want to be able to add at any index any specific value, which is, I don't know, some value. I want to be able to add this value at this index. And so what that would mean is we have to update all the indexes which are responsible for this given index, right? So while index is less than equals to n, well, first we'll obviously add the value at this index. And obviously I have not gone through the how Fenwick tree is implemented actually. I'm presuming that is something you would go through, but I'm just writing the code based on my understanding of it. So when I'm doing an add, I essentially just do a tree index plus equals to the val, and I do index plus equals to, now going to the next guy who is responsible for this index, and that's the that's all for the add. And another thing implementation that we want from this is the prefix sum up to an index, and that's something we want, right? So let's say sum equals to 0. So we'll do while index is less than equals to 0, or rather greater than 0, my bad. Sum plus equals to whatever is the value at this index, and then a bunch of bigger segments that I will get from previous indexes that I can get using index minus equals to index. And again, I would recommend having a read through or going to the previous video on what really this guy is doing. Oops. And what this guy is doing if you really want to understand, or if you're not aware of the data structure for this. But for the purpose of this, even if you don't know and if you're still trying to follow, essentially understand that this is a data structure that can give you this operation to do updates and get this prefix sums in log of n times. If this is n, then in log of n, it will be able to do that for any index prefix sum and add. And that's all we really want to use. Now, let's come to the actual solution class. And so what do we do here? So let's first find the maximum cost, right? So let's say max cost equals to 0. Now for each cost in this array, we can do max cost equals to max of cost comma max cost. So we got the max cost, right? So this is the size, the max cost, because we are indexing now based on the costs. So this n that we'll pass to the Fenwick tree is the max cost. Now we'll build two Fenwick trees or two binary index trees, one for the frequency and one for the amount. So we go tree, let's call it frequency tree equals to new Fenwick tree of size max cost, and another one called amount tree of size max cost again. Now there can be a slightly optimal ways of building these trees initially, maybe in linear time, but we'll use the n log n way and just essentially use and rely on just this add capability to just build the trees. So let's build the trees, right? So we go through each and every cost. So for each cost in A, well, for the frequency tree, what we're going to do is for this cost, I want to add 1, right? That's the frequency. And in the amount tree, Well, for this cost, this much cost gets added, right? That's the basic idea. Now that's so we have built the tree. Now what do we have to do? We have to handle the queries. So let's go through each and every query now. So for each query in queries, so let's first figure out what is the budget. So budget is query dot. The first guy is the budget, and there are broken toys. So let's see if there are broken toys. That would be query dot get one. And now let's go through each and every broken toy. So int I equals to 0, I less than broken toys or plus plus. So how do we handle broken toys? Now this is where the update is coming in, right? So now for each and every broken toy, first let's find the index of the broken toy. So index of the broken toy equals to query dot get. So it will be 2 plus I, right? So 0 is this, 1 is this, 2 and further are the indexes of the broken toys. But the indexes is 1 based, right? Based on the question, but the arrays actually are 0 based index. This A is 0 based, right? So if we want to get the index in this A array, we'll have to do a minus 1. So this is the index in the cost array. So now we actually get the cost of the toy that is broken. The cost of the toy that is broken is A of index. So this cost is something we have to remove or update in both of these trees, right? So in the frequency tree, corresponding to this cost will reduce the frequency by 1, and in the amount tree corresponding to this cost we will reduce the total amount by the same, right? And that's because essentially there can be multiple toys with the same cost, right? So we can figure out that's what this is trying to do. So we update. Now for the next like, okay, so now we'll actually process this query, but before we do the processing, or after we do the processing, we have to revert back so that the same thing is available, the initial state is available for the next query. And that's the benefit of this approach, that you don't have to do everything from the scratch. Like you don't have to build the entire trees and everything from the scratch. They're already built. We're just doing some small number of updates. And why I say small number of updates? Because the number of broken toys, which is k, is maximum 10, right? But the building of this entire tree, which can be pretty big. All right. So now we process, and after process we revert to original state. And what that would mean is you increase back the frequency, you add back the cost. So you're back at the original state. And how do we process, right? So process is something like, so essentially what we want to find out is we want to find out the cost or the first cost which crosses our budget, right? Okay, let's call this some position, right? Or let's call this as um, let's call it position. And so essentially, find first cost that crosses budget, right? That's what we're really interested in finding. And how can you find that? Based on the amount tree, is that it? And the budget, right? So we have the budget and we have the amount tree, and we'll find out using binary search. We'll find out the first cost that crosses the budget. All right, so that means that the previous cost to this, till that we can find, we can just use all the so the frequency 3 dot get position one, right? Or dot previous dot prefix sum. So this will give me all the toys till the previous cost, till the cost minus 1, right? This is all great. Now for this cost also, it could be that I could buy some toys. Like let's say for this specific cost, there are 10 toys, but I can't buy all of them, which is where like, but we could maybe buy some like between 0 to 10, right? And so to find that, let's do remaining budget is how much? Remaining budget is amount tree dot prefix sum of till the previous cost. I will have amount this. I will have spent this much money, and my original budget was, so budget minus this how is spent amount spent. This is the remaining budget. So if this cost is less than or equal to the max cost, right? That's something we have to be, because it could also be possible that when you say find first cost that crosses the budget, let's say there is no such cost that crosses the budget, then what will this return? So in that case, I'm assuming it will return something greater. That's why I'm using this condition. So if that is the case, then we'll do twice plus equals to um, whatever this remaining budget is divided by what? Divided by the cost divided by this, right? Is that fair to say? Yeah. So I have, let's say, like in the example that we are taking, we had the cost as 7 and the remaining budget was 8, right? So 8 was 7 when we could take one toy from there. And this toy, where do we add? So we have to return an array list of integer, okay? So before we run the query loop, we go array list, call it result equals to new array list, and then we'll do result dot add these toys. All right, now we have to implement this guy though still, right? The binary search to do this. So let's do that as well. So you can do that here. Before that, we have to return. So this will return the result. And we're trying to find first cost that crosses budget. So int, and we have a Fenwick tree for the amount, and we have the budget. Now there are two edge cases, right? So first edge case is, well, there is no such cost that crosses budget. That means what? That means that you can buy everything. And then what would you return then? What would you return? In that case, we'll return whatever is the maximum cost plus one. So we'll initialize this to amount tree dot n is the maximum cost. And if you can buy everything, then the first cost will be the next cost after that, but the next cost after that doesn't even exist, right? So that's fine. And the other thing is you can't buy anything. Like your budget is so less that you can't even buy a single toy. Well, in which case the first cost that crosses the budget would be something, right? Whatever the first cost is, cost one, cost two, or the first cost which has a non-zero frequency, that is the cost that crosses your budget. So that's fine. But the only thing that you really have to worry about is if you can buy everything, then you return like the max cost plus one, and which is where we'll handle this case by not explicitly using that. All right. So this is good. Now let's just do binary search, right? So what is L? Well, L equals to minimum cost is 1, R equals to the maximum cost, which is mount tree dot n. Now we just do while L is less than or equals to R. Let's find the mid. So L plus R minus L by 2. And now let's find the amount till mid. So amount spent till mid cost, right? So amount spent till mid cost is well, amount tree dot prefix sum till the mid. And now if this amount is, if it is less than or equal to our budget, that means the first guy which crosses the budget has to be in the right? So let's search further in the right side. So for that we'll do L equals to mid plus 1. Else, what is this block? this means that okay, the wherever I am at, this guy actually this guy actually crosses your budget. But is this the first guy? We don't know. There could be something in the left. So this is one candidate. So let's do can. So we'll update this to mid. This is one of the candidates, but it's also possible that something on the left is a better candidate because that's the first guy. So we'll also continue searching in the left. So we'll do r equals to min minus 1. And eventually, whatever is the smallest position that we can get, which crosses the budget, will be at that point. And at the end, we'll return position. So that's the entire logic. Let's run. I'm sure there will be lots and lots of compilation errors. Let's go through them and fix one by one. Line number 87. Okay, we missed a semicolon. Let's run and fix more. New tree. Line number 80. Let's look at line number 80. It has to be new int array. All right, what else? Missing return statement, line number 100. So we are missing, we have to return this sum. All right, let's look at the next one. Cannot find symbol. Fenwick tree, sum spelling mistake, line number 116. Okay. And finally, we are able to make it work. The first example passes. Let's submit and see if all the test cases pass or not. And all test cases pass as well. All right, let's try and think about what the time complexity would look like. All right, so what are we really doing? So we are going through the cost, right? So this is n to find the max. And then we say, okay, this is all linear. Sorry, this is all constant type. So now for each cost, for each cost means n, we're adding the cost. How much add operation takes? Log of what though? Log of the size of the tree. Size of the tree is based on the cost, which is what? Max cost. Log of max cost, right? And then what is happening? Array list result, which is all good. We're going through each and every query. So this is Q. And we're going through each and every broken toys, which is K. And for each and every broken toy, we are doing this operation, which runs in log of max cost time, right? Because our tree size is max cost. So, I mean, one or two operation, I'm not caring about the multiple as such. Then we go out of K and we're trying to find this first. All right, so I'm removing this. I'm trying to find out this first cost that crosses the budget. Well, uh, how much time that will take? We'll get this maybe from that function itself. Let's come to it from the function itself. Then we're going this prefix is sum. This is gonna take log of max cost, and again we're going amount reader prefix sum. This is gonna cost log of max cost, and everything else is fine. Reverting back to the original state. Well, it's the same as this, two times this, right? So I'm not gonna count it again. And let's see first cost that crosses budget. Well, obviously this while loop will run, we know binary search will run log of what? Log of, depending upon the size of the mount tree, which is the max cost, right? So log of max cost. And within each log of max cost, I am doing this operation, which is again log of max cost. So this function overall, its time complexity is log of max cost times log of max cost. So log of max cost squared, right? So now if we talk about the overall time complexity, okay, I'm not gonna write that here. So the overall time complexity is n plus n is fine. Then q times what are we doing for every query? I think even before that, here we will do this. So n plus n times log of max cost, n times log of max cost. Then you go for each query. What do you do? So for each query, query times. We're doing a bunch of things per query, right? So per query, first for each broken character, so k times log max cost, k times log max cost. So that will be done two times, this here and here, which is fine. K times log max cost, and then plus some operation log max cost. Okay, but that's just if you're doing something k times, then this you can ignore, right? So k plus 1 times, k plus 2 times, all good. And this one, this is also done per operation, which is log max cost squared. This is being done per query, right? So this is this plus this. So this is our total time complexity. And if we see in the question, it mentions somewhere, I forget where. That's Yeah, this expected time complexity. So if you look at it, mx I think is a max cost. So n log max cost, which is this. Obviously, if you already are at n log max cost, then this n you can already sort of remove, because if you're already n log n, then n log, if you're already some n log n, then just n plus n log n is n log n, right? So n log max cost plus q times k times log mq plus q times log m max cost squared. So it sort of matches, right? And I leave it to you to figure out the space complexity of the solution. That's your homework. All right, so that's the approach. All right, that's it.